Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 54, we would be building with Arduino, and this is part 1 of this lecture. So the different concepts that we will cover we will first introduce Arduino for IoT system development. Then we will look into the different types of Arduino boards. We will talk about Arduino Uno. Then we will talk about the different components of it, like the programmable digital pins, crystal oscillators, the connections and communications that can happen, interrupts. Then we will talk about the microcontroller within Arduino Uno, and then the microcontroller is 80 mega 328P, which for the P we will talk about its pin configurations. We will talk about the different ports and pins in detail, and finally we will just introduce the Arduino programming environment, and then we will do that in detail in part 2. So Arduino is an open source microcontroller platform which we have already introduced in our earlier lectures, and it is used for rapid prototyping of embedded and IoT applications. And once, like whenever in our lab also, when we have done that, we have first done prototyping with Arduino, and then we have moved on to more other microcontrollers. And not only that, we also have made PCBs based on our own requirements and all. Why? Because this board this open source board that we are getting here, that means it's a microcontroller platform. That means it includes both the microcontroller as well as everything else which is required to operate that microcontroller, right? So that means it's a pre-created PCB which is already we are getting, right? So, but if you want something to be customized, you want some sensors or some certain kinds of configurations in the circuit which cannot be done in Arduino, you have to build your own PCB. So that is not required at this point. So our job is to understand the concepts of Arduino or firmware, and how do we write programs for this kind of devices, or how do I select those devices, so that we can take decisions in regards to their use and optimization and so on. So Arduino is widely used due to its low cost, low power consumption, ease of programming, and strong community support, because there is so much material available in the internet. So if you decide on doing a project using Arduino, there will be no trouble finding resources in that matter. So first of all, just to reiterate what we have discussed earlier and where the Arduino fits in this particular IoT architecture. As we know, we have the perception layer, that is the device layer, where there are sensors, then there is the actuators, and then there is in the middleware, or rather not the middleware, the device, the microcontroller, and the other things which actually helps connecting the sensors and actuators, right? So that is where Arduino comes in. Then of course there is a network layer. So I may have to connect Wi-Fi module or GSM module or a Bluetooth module or a LoRa module along with this particular platform, right? So it is not inbuilt, but we can add that. And some of these versions there may be inbuilt Bluetooth module as well in this particular platform. Then the processing layer, that is cloud, edge server, the data analytics, that means where the information is sent and then what is done, how it is analyzed, that is the processing layer, which is of course beyond this capacity of a Arduino board, right? Arduino board would be sending the signals. It can do some amount of edge calculations. That means it can do some sort of calculations within itself, but it cannot do very detailed calculations, right? Because it doesn't have so much memory to store the instructions and so on. So, and then finally is the application layer, which is the dashboard, control interface, user app. So out of these 4 layers, this is where Arduino sits. And talking about closed loop IoT control, we have the physical world. We are using sensors. We can measure different things like temperature, motion, GPS, and then Arduino is the one which is processing the signal and then using control logic to decide what to do. Then it can connect to the internet via Wi-Fi, MQTT, GSM, and so on, and can send the data to cloud servers for analytics and decision making. And sometimes you receive a command back from there, and also either because of its control logic or because of some command coming back from the server, Arduino receives those, and it can actually operate some actuators like motors, relays, buzzers, and valves. So this is where the Arduino system fits in the overall loop of IoT systems or in the IoT architecture. So Arduino acts as an edge controller inside the perception layer, that is over here, and it's the edge controller, that means it can do certain amounts of processing within that as well. So there is sensors as the input and actuators as the output to this particular system. And so that means the Arduino is not just a data logger, that is, it's not only pushing data, it can do a lot of things, it can run it can change the physical environment via actuators and all. So that's why we call it a cyber physical system. So there are different versions of this Arduino boards, right? So you can see the first one is Arduino Uno. Here the microcontroller used is ATmega 328P. This is mostly for beginners and for doing basic prototyping work. And then there is a USB port over here using which you can program it from your computer, right? So you have the Arduino IDE or integrated development environment installed in your computer. You can fit it directly via USB cable with this board, and you can you write up code and you can upload it into the microcontroller, and the microcontroller will execute it. So then Arduino Mega, ATmega the controller is ATmega 2560. It is for large sensor projects. ATmega 328P again, it is used for Arduino Nano. This is a more compact IoT device, but you can use breadboards to set up your system. We will discuss breadboards in the next lecture, where you will see that it is to make sure there is not too many wires and all for testing and all. The breadboards very easily channelizes the wires connections for connecting sensors or actuators to this particular Arduino board. So it is just a way to connect the wires. At this point, that would be more than enough to understand. So then there is Arduino Mini or Pro Mini, which uses ATmega 328. It's very compact without onboard USB, so it doesn't have all the components. It has low power consumption, suitable for wearable and embedded IoT devices, right? Then there is the Arduino BT, which has a built-in Bluetooth module. Then Arduino LilyPad, which could be used for wearable IoT. And then there is also ESP32, which we can use. That means it's a dual-core MCU and Wi-Fi, where we can do much more. Where we can directly connect without adding something directly to the internet and so on. And Arduino can be also integrated with this kind of modules to enable Wi-Fi based IoT communication. So this so we can say that IoT is a sort of cloud connected edge device when it comes in this particular form. And Uno, we will be discussing mostly about Uno because we are just learning about IoT systems. And Uno means one in Italian, and it is named to mark the release of Arduino version 1. So this is the Arduino board, right? So it's a microcontroller board. This is the microcontroller. You can see the shape of the microcontroller, right? It has got all these are the different pins. This silver things are the pins, right? And then this also comes in a shape like a square with the pins, at the edge of it, right? So it could come as a square or as this sort of rectangle as well. So over here you can see the microcontroller board is based on ATmega 328P Uno, of course. It comes in different shapes and with 14 digital input-output pins. These are all different pins. So you can see these are the different pins. You can see the numbers given for each of the pins. Pin number 1 to 13. Then there is that digital ground. So together it is 14 pins, right? So and out of these 6 pins can be used as PWM outputs, right? So and then 6 analog inputs are also there. Inputs could be analog, right? So 6 analog inputs are there. And then there is a 16 megahertz clock speed oscillator. We will show that in the next slide. And this enables real-time sensing and control in IoT applications, right? So over here in the image further, if we detail out the image, you can see that this is the external power supply. I can connect an adapter and then supply power to this Arduino board. Or I can use a USB plug for sending both information as well as power from my computer. Or sometimes I can directly also connect a battery as well to this particular using the power, the different, power pins over here, as you can see over here. And then these are the analog pins which are marked over here. and this is the in-circuit serial programmer. We will learn about that. That means instead of USB, programming it via USB, I can also use another circuit which is called a bootloader to load a code inside this particular microcontroller via the in-circuit serial programmer. Now, why this is important? Because in some, if I use it for making a device or something, then plugging it to a USB and putting a computer, it sometimes may not be convenient. So we can use another, bootloader or circuit which we connect, and we can use that bootloader to load the code in many of this particular products or circuits that we will build, right? Product means that circuit, this particular board would be inside that product, right? There is a reset button, of course, which allows us to reset the system. That means reset over here means the code within the microcontroller would be again read and run, right? So it will not, it will stop the previous execution and then start fresh. And then there is serial out and serial in. So this is for reading, writing messages or sending serial, commands. And then there is the then there are the voltage in. This is 5-volt power pin using which I can supply power to some sensors or some actuators. This is the ground pin, and then we can also reset it, using a signal instead of physically pressing it. And then 3.3-volt power pin, that also we can, that is also provided. So each digital pin can be used as an input or output using pin. We have to, of course, code, will it be used as an input or output in the IDE? That is, when we write program in the IDE for this particular microcontroller, I have to say that which pin would be used as input or which pin would be used as output. And we use this function digital write and digital read to, read or write whatever we want to do. Each pin operates at 5 volts and can provide or receive a maximum of 40 milliamperes and as an internal pull 40 milliamperes. So if you require more than that for that sensor or something, then I have to send it via this 5.5 volt power pin or 3.3 volt power pin and so on. And then this pins has not all, but some of these pins have got internal pull-up resistors, which basically means that and it basically means that always the pin is at a high state, even though nothing is connected with that. Now, it is kept at a higher state. Otherwise, it would continuously fluctuate between on and off. That it will become high or low, high or low. To prevent that, we keep it high. Sometimes we require that so that if it is sensing something, it actually helps, right? Without power also, if it is already high, then we can make sure that if it is turned off or high, then we can understand that change that is happening. So this is how we do a program for the Arduino. So we will of course discuss this in detail in the next lecture. But the structure of our Arduino program is like this. We have two functions, void setup and void loop. The first part is the setup code. That means this part will run once, and then the void loop, the code that is put over here, would be run repeatedly one after another, right? So that means it would be continuously executed in a loop form, right? So that means void setup is for setting up which pin is going to do what and declaring variables and all these things, and loop is for running the code, because in a device the code continuously runs, right? It is not like a program where we compile it and then we execute it once, or our interpreter just runs it once and it's done. So in this case, because it's a device, the code is always active, right? So it continuously runs in a loop form. So that's why it is given the name void loop. So digital pins could be either inputs or outputs. It can read or write digital signals, either zeros or 5 volts. And we have to give the right command to do that, right? So the first command is to define, within void setup, is to define the pin types, right? So first I type in a variable name and give it a value, like, if it's an integer, depending on what thing we are recording, it's an integer because we are trying to identify which pin it is. So pin mode is the name of the function, pin number for whichever pin I'm trying to identify, and then the pin type has to be given, right? So that means over here I declare int lead as 13, and then pin mode equal to lead and output. That means I cannot give 13 directly, I give the variable name, that is 13, and then this is the output. So this pin number 13 would be for output, not for input. So pin 13 is a LED connected on most Arduino boards. It is by default a LED is connected. So if I go back So you see there is a LED over here. So there are 3 LEDs. The test LED, which is 13, which is by default it is there. Then TXRL, if some serial communication is happening via this, information is being sent, then this particular TXRX, LEDs burn, and then there is a power LED. If there is power, it will glow, right? So these are the 3 LEDs which is already fitted in the board. So pin 13 has a LED connected on most Arduino boards. So if in 13 I want to, run it, first in setup I will initialize the digital pin, like pin mode LED output. So that means we are saying that it's the output pin. And then in the loop, what we will do is we will say digital write, digital read we can do, digital write also we can do. So digital write is LED high. That means that the value of LED would, that means first of all the which pin we have to refer to, and should I turn that particular pin high or low, because it's a digital signal, either it will be high or low. So Arduino can turn a pin into high or low, right? So over here when I turn it, make it into high, and because it's the output pin, it turns the LED on. That means high is the voltage level in this case, right? After that, my next command is delay 1000. Here 1000 means 1 second, right? So delay 1000 means wait for 1 second. That means once it glows, it will wait for 1 second, and then it will say digital write LED low. So then it will turn the pin to low value. Low means it turns the LED off by making the voltage low. So then again give a delay of 2 seconds, 2000, and then again it will keep on going in a loop. So then again it will start digital write. So it will glow for 1 second, then turn off for 2 seconds, and it will keep on continuously doing it. So as you understand, we also, some of the digital pins in Arduino are also PWM pins, particularly pin numbers 3, 5, 6, 9, 10 and 11. And as you know, PWM is a way to produce output digital voltages whose effect is similar to analog voltages, right? So that means in the instead of saying just high or low, I can give a periodic pulse signal, but that means for a certain time I can send 0, 0, zeros, and that actually governs the duration, governs that what should be the voltage level or which we are trying to push, right? So this concept we have already explained earlier. This is the concept of duty cycle. It is the percentage of time the signal is turned high, and within a full cycle, of course, and we can have 25%, 78%, 50% duty cycles, and this is how it will looks in an oscilloscope, that particular signal, right? So this here what we are defining is constant INT LED pin equal to 9, and in the setup pin mode LED pin is the name of the that variable, that is 9, of course. This is set as output, and then in the loop, void loop function, what we are saying is we want a brightness of 50%, right? And now PWM signal, because it is it could be a series of bits that we can send. We can have zeros to we can have a series of for that particular time period. I will keep it on for a certain amount of time, and depending on the number of that values we send, we can have it from 0 to 255. Now this is again the concept of 2 to the power 8, and then from there we are getting 256, and we have a total range of values that we can generate by giving this how long I can keep that particular signal open in the PWM. In this case, if it is 50%, I will give 128 out of 255, right? So in this case, I will give the value of 128. So that means it is 50%. So analog write, so that is digital write. Similarly, there is analog write, LED pin 128. This is 50% duty cycle, that is medium brightness, right? So once we do that, then it will glow to 50% of its level. And then again delay is 1000, same as earlier, and then again we can turn the LED to, we can make the LED as 0. 0 in this means it is not actually glowing at all, right? So in this PWM, the signal is from 0 to 255. Even in motors and all, we can control the speed using the value from 0 to 255. So that's the range within which we can adjust the value to determine what percentage would be this signal turned on, right? So this analog write LED pin 0 actually turns off, then there is a delay of 1000, and then again the entire loop starts, and then we have analog write LED pin 128, again it will grow to 50% brightness. So now coming to the other components of the board, you see over here which is marked in red, This is the 16 megahertz, of course this is a 16 megahertz crystal oscillator, and the job of the oscillator is to provide precise and stable clock signals, right? And how it does it is there is a crystal inside which resonates at exactly 16 megahertz when power is applied to it, and this is the property of that particular crystal. And the ATmega 320P uses the signal coming out of this crystal to synchronize all internal operations such as executing instructions to handling timers and serial communications. Why? Because that signal comes and we can, that is precise, that, that vibration that is happening, that that happens over a period of time, right? The number of vibrations that happens from there, we can make out that what is the time passed and so on, right? So that information is utilized to determine that, okay, what sort of the timer instruction that we are sending to the command to the microcontroller via the microcontroller is sending a command to the pin saying that keep it delay for 1000, right? That 1000 is what? That 1000 is a time, and that time, how it determines, if it doesn't have this, this sort of a clock built in, right? So that's a mechanical sort of a vibe system which generates the time that is required to run this kind of circuits. So a consistent clock ensures accurate timing. We use the delay function or millis function to actually determine some time periods and so on. And the communication protocols, we will learn about this even after this, serial communication, I2C, SPI, all these communication protocols uses that signal coming from the oscillator to determine that what is the time gap between when signals are sent or not. Same with PWM signal generation as well. The clock speed 16 megahertz also talks about, that means the microcontroller receives 16 million clock cycles per second, right? That vibration, and each clock cycle allows the microcontroller to perform one basic operation like fetching or executing an instruction. So a 16 megahertz clock means that Arduino Uno can perform up to 16 million simple operations per second in this particular case. Now we will talk about other connections. So we have one USB connection over here, one power jack over here, a reset button over here. The operating voltage is 5 volts. Input voltage is 7 to 12 volts, which is recommended. It can take more or less, but this is recommended. Input voltage can also be something around 6 to 20 volts. That's the limit. We shouldn't go beyond that. So we can also connect a battery as well. So the adapter can be connected by plugging a 2.1 millimeter center positive plug onto the board's power jack. So this is a typical adapter. We can connect via an adapter this particular board and get power using that adapter. And leads from battery can be inserted into the ground and the V pin, voltage in pin headers to power this particular board, right? The board can operate on an external supply of 6 to 20 volts, but below 7 volts it may become unstable, or as the 5 volt output that is supposed to come, that would get dropped, and above 12 volts the regulator may also overheat, right? So that's why the range is limited to 7 to 12 volts. Now coming to communication that happens, we have this serial 0RX and 1TX. This is the pins over here. This is used to receive and transmit serial data. These pins are connected to the corresponding pins of the ATmega 8 this U2 USB to TTL serial chip. So this is not the ATmega chip, there is another chip. So this RX and TX pin is connected to that particular chip, which is also part of this particular board. And what it does is this ATmega 8 U2 USB to serial converter. This is of course not the main processor, but what it handles the USB communication and converts it to serial signals that the main ATmega 328P can understand. That means it will take the values and it will convert it into serial signals, and this allows any computer and reader to talk to each other smoothly via the USB cable. Then there is something called interrupts. That means any kind of circuit sometimes require interrupts. For example, suppose, for example, in one of our products, where we have developed a system where there is an accelerometer connected to an Arduino, and if somebody moves that particular system, immediately it wakes up the microcontroller. Usually the microcontroller in a state of sleep, or sometimes what happens if forget state of sleep, it may wake up some other sensor, like for example like a GPS location. That means somebody moves that particular device or that particular machine, then it will start connecting to the internet, or it starts connecting with the GPS signal or GPS chip to get the signal. Otherwise, if I keep all of them turned on, it will draw a lot of power. If I want to limit that, I can use an interrupt, right? So interrupt means this there are some of the pins connected in such a way, that means few of the pins of microcontroller, that it could be configured to trigger an interrupt on a low value, or a rising or falling edge, or a change in value, right? So that function is attach interrupt function. Now what it does is, suppose I have an accelerometer connected, right? Nothing is happening. Now somebody moves the device. That accelerometer will govern, will detect some changes happened in the signal, and as though that accelerometer would be connected to the interrupt pin. And if that is connected with the interrupt pin actually understands some changes happened, and when that change has happened, it will do some actions, right? So digital pins 2 and 3 on most of these Arduino boards are used to detect and respond to external events asynchronously, right? And allows the microcontroller to immediately react to changes like rising or falling voltage without constantly checking the status on the main loop. So I can write code in the loop saying that check in this pin, check if it is high or low, and then get a response, right? But in this case, we are not doing that thing. Automatically, if there is a detection, if it detects some change in that voltage or something in that value, then automatically it sends a signal back. So it doesn't need to be specified separately. So this is called event handling. That means some external events could be handled in this way, right? So so while some other tasks are being done, or the microcontroller is in sleep mode, the interrupt will signal the processor when attention is required. So that's why we call it that there is some event happened, so we have to handle that event. So it could be a button press, that means somebody presses a button. It could be a sensor trigger like a PIR motion sensor, right? Somebody has entered into your house to steal something, so that could be determined. Then counting pulses from a tachometer, like rotation, the speed of something, right? It could be understood from there. If something odd is happening, then it can report. Then detecting changes from external communication lines. Many things could be, we can use an interrupt to detect some change in the signal automatically, right? Without writing a code to check it again and again, right? So if I keep the code running, then the processor cannot go to sleep mode, and we will keep on consuming power, right? So that is why if it goes into sleep mode, but the interrupt is active and something is detected, immediately we can start. Then there are SP1, this is this serial peripheral interface. These pins are also there, and this pin supports SPI communication. This is pin number 10 SS, 11 MOSI, 12 MISO, and 13 SCK. So each has got different tasks, of course, but the primary job they do is they allow full duplet communication, means both side communication. Information is sent and also received for high speed data exchange between a master, which is Arduino, and one or more slaves, which are sensors, displays, and so on. So that means sometimes sensors needs to connect with send some data. It's not only the pin being high or low, some data needs to be exchanged and all. So that is where this SP1, SP2, this sort of pins comes in, right? MOSI is master out, slave in. Master sends data to slave using this pin. MISO is master in, slave out. Slave sends data to master. Then SCK serial clock signal from master. Some of the sensors require the clock signal as well, so that accordingly it will act based on the time. So that's why this is there. Then SSCS is slave select, chip select, selects which slave to communicate with active low, or how to select in which way which one to communicate out of many slaves, right? If there are many slaves connected. So these are also different ways to communicate. And but here it is mostly for connecting with sensors, not via the USB cable like earlier what we were seeing, but directly using this particular pins. Now coming to the microcontroller itself, we see that I explained earlier, either it could be a rectangular form, it could be a squarish form. It is this ATmega 328P is used as a controller in Arduino Uno. Arduino Uno is that processing board or that motherboard, you can say. This is the main processing unit in that particular Arduino product, Arduino Uno, and it is a high performance low power processor where it's a AVR 8-bit microcontroller, and of course we don't need to go in too much details about it. It follows advanced RISC architecture, reduced instruction set computing, means the design uses small and efficient set of fast instructions for high speed and efficient execution. So there are 131 powerful machine level instructions, 32 registers in it. Each one has got 8-bit wide space for data processing. Then about 20 MIPS, million instructions per second, throughput at 20 megahertz clock speed. Depends on this microcontroller can operate at this, but the board can operate at 16, which we saw earlier. Then it has got a little bit of memory over here, non-volatile memory segment, so it can store the data. That means it will store that that code that we load into the microcontroller, that will stay there inside. So 32 kilobyte of in-system self-programmable flash memory is there, and 1 byte internal SRAM is there for processing, and 23 programmable input-output lines. So we can, including digital and everything, analog everything, and it's a programmable serial USART, that kind of transmitter is also there. So USART is basically universal synchronous or asynchronous. If it is synchronous, that means the clock signal is also there. Asynchronous receiver transmitter, it is a part of it is the programmable part hardware module used for serial communication between a microcontroller and external devices, right? So it is programmable, means we can change parameters such as baud rates, data bits. That means when we have to have Bluetooth communication or some other forms of communication, we have to set all this, right? What form of communication is happening, right? And we can also set will it happen in synchronous mode or asynchronous mode, right? And we can configure that. And this transmits and receives serial TXRX data, converts parallel data to serial and vice versa, and supports full duplex communication. That means both side communication. So usually we use this USRT port for serial monitor, GPS, GSM, Bluetooth, this kind of sensors, whereas SPI is used for OLED displays, SD cards, high-speed sensors, ADC and DACs, and so on. So this is the pin configuration of the microcontroller that we are using, that we just demonstrated. So we have talked about all the different pins. So either it could be in rectangular form or square form. We will talk about the pins. So this is ground, this is VCC, and then this is the different P the P group of pins. Then there is different over here. This AVCC is over here. So you see this, every one of them are listed, and each of them has got some task, like this is RDX, TXD, this is for serial communication, right? So there are different pins, and each pin is used for different purposes. So coming to the different other ports and pins which are connected. So as we have the IC SP header, which we discussed earlier, that is the in-circuit serial programming header, which is a 6-pin, sometimes 5-pin connector used to program the microcontroller directly. So I can send a program to the microcontroller via the USB, or we can directly put it into the microcontroller using a bootloader, using this particular set of pins over here, right? So this is we have also VCC, digital 5-volt supply voltage, ground. Already we have talked about this earlier. Then we have got analog supply voltage pin, AVCC. There are so what it does is it is a power supply pin specifically for analog to digital converter. And even though the digital pin part of the microcontroller runs on VCC, the ADC module use AVCC, right? So anyway, these are more specific technical details. So in most cases, we will need to understand them in deeply when we are going to create the circuits for certain kinds of sensors. And according to the specifications of the sensor, we know exactly how to connect it to the microcontroller. Then there are pins PC0 to PC5. These are port C pins, 6 general purpose input output pins. It has got internal pull-up registers available for each pin, so it could remain in the high state. And so it is used for different, because it is always in the high state, that means it is good for power sensitive safe start situations, that means we can reset and all. And then there are port B, which is 8 general purpose digital input pins. Here it is this pull-up registers are optional, and sometimes one of them PB6 has a special role in oscillator and clock system. That means whenever we want to send a clock signal, we can do it via that pin. Then PBC6 is the reset pin. It is mostly the reset pin, but we can use it for a general purpose pin as well if we want it. In that case, the reset pin ability will not be there. And then more or less this is this pin port D, which is D7 to from 0 to D7, which is again 8 pins, and this can be again used for different things. That PD0 and PD1 is for UART RxTX, PD2, PD3 is for external interrupts that we have discussed earlier. Then D4, D5 is digital input output, D5 is PWM output, D6 is PWM output, D7 is digital input output. So finally we come, once we know the microcontroller, we have done sensors earlier as well in the previous lecture. So now we know how to connect the sensors, but we will give more detailed demonstrations in the next lecture to show how to simply connect a sensor to a microcontroller board, and then we have to create a program for it, right? So we already have seen the structure of the program, which is void, and then there is a loop. So these are two functions there, and we code this in the Arduino programming environment, right? So this is the Arduino software ID, which is free. You can download it, and you can just Google it, and you can download it directly. And then we have to select what board are we using. Accordingly, the code will be created, and then we can compile the code, and we can burn the code into the into the microcontroller itself. So ATmega 328 on Arduino Uno comes with a pre-burned with bootloader that allows upload new code to it without use of external hardware programmer. But sometimes we can, if I use the ICSP, that in-circuit serial programming header, then we have to use a bootloader, which is another circuit through which we can put in the code into this particular, into the this hardware, right? So Arduino ID works on Windows, Linux, Mac, in all platforms, and what it does is it allows us to do the coding and then push the coding into the microcontroller as well. So we will give demonstration of that in the next lecture. So these are some of the references that we have used. To conclude, Arduino acts as an edge controller in IoT systems, integrating sensors, processing, communication and actuators to enable real-time sensing, control and closed-loop cyber-physical system development. Thank you.